we can see the behaviors of light and how it causes objects to bend in two different ways. Check this out. First is a nice straight meter stick. Now the meter stick sure looks bent as it goes into the water. Now it's not physically bent, but it sure looks bent. Another way to show the bending of light is by trying to stab at some of these washers. By aiming at the center of the washer, check out what happens. I come up short. Now, time and time again, if I were to repeat this, I would always come up short. We've been talking about a lot of stuff so far, so I think it's time that we start bringing all of this together into some meaningful, applicable expressions and make it useful for us. We began by talking about several demonstrations and created some ray diagrams and got some terminology under our belts and got an understanding of what it meant to be refracted, which is to be bent. And we also got that understanding of the fact that light slows down, or at least changes speed, when it passes through another medium. Now Snell, with his observations, related the angles of incidence and refraction to the speeds, and we just finished talking about the characteristics of the wave and how the frequency must be the same in both media to explain the physical observations that we're making. And so let's bring all of this stuff together into a single expression. Well, to begin with, I want you to recall our definition of wave speed. We defined wave speed as being defined by lambda f, the wavelength times the frequency. So that's how we define wave speed. Now for the frequency to be the same in both media, as we just established, yet have the speed of light in the second medium slow down, like we saw on our carpet demo here, when in one medium it slows down when one wheel catches a more dense traveling substance, it slows down. So for the frequency to be the same in both media, yet slow down in substance 2, then the wavelength of light must change. It must get smaller. Now, everything that we're going to produce right here is for one particular case, and that case is for N1 being less than N2. Of course, everything we talk about will be reversed if N2 is less than N1. Okay, so I just want to make note that everything we do is for the case of N1, for case N1 less than N2. Okay, so one more time before we start writing anything down. For the frequencies to be the same in both media, yet have the light slow down in the second medium, then the wavelength of light must get smaller. Has to, by definition. Okay? And so let's bring all of this together then. All right, so to describe the speed of light in medium 1, we'll use V1, okay, is equal to lambda 1 f. Okay, so this is the speed of light in medium 1. This is the wavelength of light in medium 1, and this is the frequency that it's traveling. The speed of light in number 2, in medium 2, will be lambda 2 f. Speed of light in medium 2, wavelength of light in medium 2, frequency. Now notice I didn't subscript them because the frequency is the same in both. Okay, well, if the frequency is the same in both, then V1 is proportional, or V1 is to lambda 1 as V2 is to lambda 2. And now we can set these two equal to each other. Also remember that we can define or redefine the velocities in terms of the index of refraction. So recall that the index of refraction was equal to c over v. So if I solve for v, it would be c over n. So now I can take my velocities here and now turn them into an understanding, or relate rather, the understanding of the index of refraction. So that would turn these two terms into C n1 equals C n2 lambda 2. Okay? And now it's just some algebra and some simplification. We see the C's divide out, and we end up with 1 over n1 lambda 1 equal to 1 over n2 lambda 2. All right, cool. Now, cross multiplying and flipping this around, we can see that n1 lambda 1 is equal to n2 lambda 2. Cross multiplying both sides and then flipping it around so the 1's are on the left and the 2's are on the right, we end up with a relationship that relates the index of refraction to the wavelength of light that's passing in, or rather through, that particular medium. So this relationship right here, it has no name, but it does relate. It does relate the index of refraction to the changes in wavelength. So it relates indices of refraction to the changes in wavelength. Okay? So this is a very important relationship. Again, we've made lots of observations here. We know that the different medium play different roles. We know that the wavelength obviously changes in different medium. We know that the speeds obviously change in different medium. We know that the angle of the angle of refraction and incidence also vary when you encounter a different substance. So there are lots of things to relate here, and this is one very important relationship because it relates the index of refraction to the wavelength of light passing through each of those different medium. Okay, well, there is a special case. This is important, absolutely, and it's from this point that we talk about a very special case. And that case is when light is incident in a vacuum or from a vacuum. So let's take our understanding right here and whittle it down to a very common example that we see. Most light is incident in a vacuum. Now recall the indices of refraction that I put up on the board here, and vacuum and air were both seen as having an index of refraction of 1. That is how we see light and its interactions most often. We usually have light incident in air or in a vacuum. So let's talk about this case, and then this will help us understand a little bit more about the significance of this relationship between the index of refraction and the wavelength.